we will start with the coordinate system. For sure, if you are, and also we talk about the parameterized curve, because you have a curve. If you have a curve, you are in the 2-dimension, right? So this is a 2-dimensional one. The rectangular coordinates or Cartesian coordinate in 2-dimension is x and y, right? But in the 3-dimension, you have x, y, z, right? Okay, this is a rectangular coordinates. All of us heard about it and know what is the relation between x and y. This relation, we call it one variable function, right? So here we have y as a function of x, right? In the other side, we have z as a function of x and y, right? So again, here we know in the first quadrant, x and y are positive. In the second quadrant, y is negative and x is positive. In the third one, both of them are negative. In the quadrant number 4, x is positive and y is negative. Because this is the side of positive x, this is the side of negative. Up is the positive for y, down is the negative for y. Okay? So you have here x, y at this one here, in this plane. And you have xz and you have yz as well, right? So you have a special case of 2-dimension is already here, right? Okay, so this is the coordinates everyone knows about it, right? But later on, we cannot deal with someone going around or rotating or go through a circle or going through parabola, right? Not a parabola, sorry, with ellipse. So you go in angle, right? So you have a polar coordinate. In the polar coordinate, x is r cosine theta, and y is r sine theta, right? This is a relation between the Cartesian coordinate in 2-dimension and the polar coordinate, right? We have another polar coordinate in 3-dimension. To be honest, we have two polar coordinate in 3-dimension. One of them is a spherical coordinate. In the spherical coordinate, you have r and phi and theta. This theta exactly the one in the polar coordinate in 2-dimension, right? But the new phi is here. This is a new phi. So phi here is exactly like theta in xy, right? Yeah, because it is an xy coordinate. So you have two angles in the spherical coordinate and one distance, right? Okay, now if you would like to change from the spherical to Cartesian, you use this relations, right? So you have rho, the radius we call it rho in the spherical, not r, like the polar, and you have these two angles, right? If you would like to change from Cartesian to the spherical, you have the relation between these two because you have x, y, z, right? This is why I start with the Cartesian or rectangular coordinates, right? So now, if you have x and y and z, you can have r theta phi. If you have rho theta phi, you can have x, y, z, right? Okay, why I'm teaching you this one? To be ready for the surface integral, because we don't have a surface in 2-dimension. We have a curve in 2-dimension, right? But in the 3-dimension, we have a surface. If you don't know the equation of the surface, we cannot integrate, right? So we have to start with, okay, the line element in the spherical coordinate, which is, do you remember, r or ds, that this is the distance element or the line element is dr, r dr, r d theta, r phi d theta. So this r phi theta is the unit vector exactly corresponding to I and j and k in the rectangular coordinates, right? The area element In the Cartesian, the area element is dx dy, right? This is the Cartesian area element in the Cartesian, right? But the area element in the polar, the be r dr d theta. Okay. Why this one? Because this is the area element in the polar. This is r. This is d theta. Okay. We know the length of this one is r d theta, right? So when you have r times r d theta, so you have r dr. This is, we call it dr, right? So if you have the area element in the polar, so the area element in the polar is r dr d theta. You have to know all of these one. So area element in the Cartesian 2-dimension dx dy. Because why? If you have area element like this one, this is dx, this is dy. What is the area of this rectangle? Dx dy, right? If you have a sector of a circle like this one with a small angle d theta and small length dr, okay, we know the arc length is r d theta. So the area of this one is r dr d theta, right? Now in the surface, the area element supposed to be in the 3-dimension, right? So you have this is 1, 2, 3, right? So this is the area element. You have r and phi and theta, right? The volume element, it has d theta, d phi, dr, right? The area element has d theta, d phi, right? Which is fair enough. The area element is a unit square, right? The volume is unit cube, right? So you have 3 units multiplied together, so you have unit cube. Here you have 2 units, it will be unit square. If you would like to remember it in this way, right? But here you have only one unit. Okay, so because you have line elements, okay? Do you remember the Jacobian? The derivative, the partial derivative, right? So the Jacobian, or you can call it the value in front of d theta d phi, right? This is why they got r squared sine phi. R squared sine phi coming from the derivative with respect x, y, z with respect to r theta phi, right? You have this relation, right, between x, y, z and r theta phi. So x as a function of y, you have it, right? Before this one, I'll show it to you. Sorry. Yeah, you have x, y, z in terms of r theta phi. So you can differentiate x, y, z with respect to r and theta and phi, right? So you can also find, so you know, r squared sine phi is coming from the Jacobian, right? Now, do you remember the nabla? Nabla in the Cartesian, what is the nabla in the Cartesian here? Nabla in the Cartesian was partial by partial xi, partial by partial yj, if you remember this one, partial by partial z, k. In the spherical coordinate, I don't have ijk, I have r and phi and theta, right? I have the unit vector with respect to r, the unit vector with respect to phi, and the unit vector with theta, right? So this is your nabla in the spherical coordinate. Remember this one, right? Okay, good. Now we go back. I will erase this one just not to confuse you. We came back to the polar again. This is what I told you, right? In the polar coordinate, you have the line element, the r squared. You are looking for only the area element here. Is r d theta as I showed to you, right? If you have any curve represented by the function r as a function of theta, because we are doing in the polar coordinate. If you are in the Cartesian, y will be function of x, right? But in the polar, r will be r function of theta. Any area for any enclosed by the polar curve r equal is coming from this formula, right? So all the time in the polar, you integrate with respect to theta angle, right? To cover the whole curve. Because this is, they call it the pole, if you remember, right? Sorry, this is, they call it the pole. Okay, and this is, they call it the polar line. Okay, this is the origin. In the Cartesian, they call it the pole, right? And the x-axis, the positive x-axis, we call it the polar line in the polar coordinates, right? Now, I'm preparing you to go through the double integral in the polar coordinate. So you are going to use the polar area element, dA equal to r d theta, dr d theta. And also you know that nabla in the Cartesian. So you have to know nabla in the spherical, right? And later on, you will know it in the cylindrical coordinate. Catch all the points? Okay, good. Now, let's go for the other polar coordinate in the 3 dimension. It's called cylindrical coordinate. Why we call it cylindrical? Because all the time when this one theta rotate, it will build up a circle, right? The z in the Cartesian is the same z in the cylinder. So you have a cylinder with a circular base, right? Okay, good. So this is how to change. If you have x, y, z Cartesian, you can change it into cylindrical one, right? Why we don't have z, Alan? We don't have z because z is the same as z in the Cartesian, right? Okay, and if you remember, x, y here, you have r and theta similar to the polar coordinate in the 2 dimension, right? So the cylindrical coordinate is the mix between 2-dimensional polar coordinates. Again, the cylindrical coordinate is a mix of the polar coordinate in 2 dimension here, x, y, plus the coordinate z in the Cartesian, right? This mix gives you the cylindrical coordinate. So all the time you are given x and y. Why you are not given z? Because z is z. No. Z in the Cartesian is the same as z in the cylindrical. The same coordinate. The same coordinate, Ahmed. Okay. So no need to think about z. Z is the same as value as the z in the cylinder. Okay, now you can hear me? Good. So the same z in the Cartesian is the same as, this is Cartesian. This is the Zn cylinder, right? Okay. This is exactly like the polar coordinate in the 2 dimension, right? Okay. So if you have r and theta, you can find x and y, and z is the same as z, right? If you have r and theta, you can find x and y, right? So vice versa, you can find everything here. Also, you can find the line element is here, right? What's r, theta, phi? This is the unit vectors, right? What is the unit vectors in the Cartesian? xi dxi plus dyj plus, this is a line element, right? Okay, this is exactly like what, Alan? dr, right? Because r is xi plus yj plus zk, right? This is what we have done last lecture, right? Okay, now what is a volume element? Why we didn't say area element here? Because we are in 3 dimension, right? So we are caring about the volume element, right? The volume element in the Cartesian is dx, dy, dz, right? The length times the height times the width, right? In the cylindrical, dv is equal r dr d theta d phi, right? Here is the Jacob dv, or the volume element. Okay, the volume element, right, is r dr d theta dz, right? This is in the cylinder. The Jacobian is you differentiate x, y, z in terms of r theta z, because you have the relation between x and r theta z, right? Remember, again, your nabla in the cylinder coordinate is this one, r multiplied by rho partial r partial by partial r, the unit vector theta, 1 over r partial by partial theta, the unit vector in the direction of z, partial by partial z. So this is all what you have to know in each coordinate, right, system. Catch it? Good. Now, we are doing all of these one to be ready for what? First of all, if we have a line integral and we would like to change it into double integral, we need the area element in the 2-dimension, which is r dr d theta in the polar, right? Because sometimes we have to change the double integral from the Cartesian into polar, especially when we have closed curve, like circle, right? Or ellipse. So when you have a circle or ellipse, it is better to use a polar coordinate in 2-dimension, right? If you have cylinder, it is better to use a cylindrical coordinate. If you have a sphere or part of a sphere, it's better to use the spherical coordinate. This is why you have to get an idea about the coordinate systems. Catch it? Let's go. What does it mean, the parametric equation, right? So it means you have one parameter. Yeah, okay. Let's go for this one. If you have a segment, right, between A and B, 2 points, this is your function of x in this interval, right? How to write the parametric equation of this segment? As I told you, consider x equal to t, right? Now, you substitute x by the new value t, so your function will be coming as a function of the parameter t, right? Let's go for this one. This is also give you, if you have x as t plus 1, right? This is the segment. All of this one, in general, for the segment from A, say, this is from x naught, y naught, z naught, to another, any other point, right? X, y, z. You have to find the direction from these 2 points, right? The direction is a vector, right? We are in 2-dimension, right? So this vector, yeah, no, we are talking about y as a function of x. It's 2-dimension, right? So you have a direction represented by a vector, right? This vector, we call it A and B, say, right? Call the coordinate for this direction A and B, right? So the segment, or the segment parametric equation, will be what? X will equal to A t plus x naught, y equal to bt plus y naught. Easy? Okay. So you put in front of your parameter the coordinates of the vector from your point to the other point, right? So this is the parametric equation in general for any segment, line segment, right? Okay. Let's go for another example here. Do you think, what is this equation represent, Alan? it is easy to move this one to the other side, just to be easy for you, and get x to the other side. So 1 minus x. When, oh, sorry, you keep x, no, sorry. Yeah. You can write it like this, or it is better to write it like this one. So when you have something squared and have something not squared, it means you have a parabola, right? Parabola with which is the main axis for this parabola? The one is not squared, right? So if you would like, yeah, go ahead. It's okay. I take minus as a common factor just to put, what is a parabola equation? If you have y squared equal to x, this is a parabola equation with the origin as the head, right? Okay. And here, if you would like to graph it, you will graph it because y is squared. So for each one value of x, you have two value for y, right? So this is the equation represent this parabola, right? If you have x equal to a y square, in this case, your parabola is vertical one, right? Because for two value of y, you have one value of x. Okay? Okay? If a is positive, it will be up. If a is negative, it will be down. In this case, a is positive, you'll be to the right, okay? A is negative, will be to the left, okay? Now you know this is a parabola, right? This is a parabola equation. So as I told you, it is easy to let x equal to t or y equal to t. It is easy now to let your parameter x or y. It is better to get rid of the square root. I don't care about the positive and negative, so I take y as t, right? Okay. So if you let y as your parameter, so the parametric equation would be what? x1 minus t squared, right? Now you know how to change the Cartesian coordinate into parametric equation. In two dimension, as I told you, you may have x as your parameter t, or you may have y as your parameter t, right? So now you know how to change your Cartesian coordinate into parametric equation by letting x equal to your parameter t or y. It depends on your curve equation, right? It is better to get rid of any one squared, right? Any variable squared, it is better to let it t, just to not to be confused between positive or negative values, right? But if you have first degree, no problem if you let x equal to t or y equal to t. But if you have a square, it is better to get your parameter as the squared one, right? Now, this is the ellipse, right? We know the ellipse equation in the Cartesian is x squared over a squared plus y squared over b squared equal to 1, right? We know the link between the Cartesian and the polar, x equal to r cosine theta and y equal to r sine theta, right? Just plug in this one here. What do you have? This is a, sorry. My radius is a, and sorry, I make a mistake. Because you have two radius. In the ellipse, in the circle, you have one radius. In the ellipse, you have two radius, right? The longer one and the shorter one. So you have a here, b. So it will equal 1 or not equal 1? It's equal 1, right? So the left-hand side will equal to the right-hand side up to the polar coordinate conversion, right? Easy? So what is the parametric equation for the ellipse? The polar is exactly like the polar coordinate, right? This is why I gave you the polar coordinate system from the beginning, because it is linked to the parametric equation, right? Now you know the parametric equation for the Cartesian. You let x as your parameter or y is your parameter, depends on. If you have a first degree, no problem to have x as a t or y as a t. If you have anything squared, it is better to have the squared one as a parameter, right? When you have a polar coordinate, any circle, any ellipse, you use the same thing. The difference is, if you have ellipse, you have two radius, right? A and B. If you have a circle, you have one radius, right? So now let's go for the parabola, right? We are in two dimension. We're still in that. Yeah. Here in the parabola, you don't have cosine and sine because you are not going to rotate around, right? So you have cosine, the hyperbolic functions, right? The same thing as the ellipse, but you add h for hyperbolic function, right? This is a parametric equation for the hyperbola, right? This hyperbolic in cosine terms, right? You know, cosine t is equal to what? Half of the sum of et to the plus e to the minus t, right? And sine is half of the difference between e to the power t and e to the minus t, right? And you know, this is exactly similar to the trigonometric one, right? But in the trigonometric, you have plus cosine square plus sine square theta equal to 1, right? This gives you a circle, right? This gives you hyperbola, right? This is why this one, the trigonometric one, give you a circle. This hyperbolic one give you hyperbolic function, curve, right? So remember, in the ellipse here, you have a cosine t, y equal to b sine t. If you have a circle, you have one radius a, right? So the parametric equation for the circle will be a cosine t and y equal to a sine t, because I have one radius, right? Because r equal to a. Here in the ellipse, I have two radius, right? In the hyperbolic, is the same as the ellipse, but you have to be in the hyperbolic functions, right? And you know what does it mean cosine and what does it mean sine? Okay? Now, you can write the hyperbolic in the trigonometric function, right? Okay, so this is another parametric equation for the hyperbolic, right? Okay, because there is a relation between the trigonometric and the hyperbolic function, right? So you can use this parametric equation, or you can use this parametric equation, right? Or you can use the original one, which I prefer this one, to be honest, right? Okay. Now, to using the surface integral and the polar integral, right? Okay. Here, this is the parametric equation. R is given in terms of the two parameter s and t, right? The first coordinate is x, right? The second one is y. The third one is z, right? Okay. If you have another example here, r is minus 3 plus s, another parameter equation, right? But do you think this one is similar to this one? It seems not. It seems not, because the first coordinate is different from the first coordinate here, right? But if you add the first coordinate plus the second one plus the third one, you will have both. You have one in all of this one. Add this one plus this one plus this one. What do you have? You will cancel out t with t and s with s. What's left when you're adding them? 1, right? Add this one to this one to this one. So what do you have? You cancel. You have t here, okay, and another t here. So 2t will be canceled out with minus 2t, right? What is s? You have minus 3s, and you have plus 2 and plus 1 here. So this 3 will cancel with the negative 3, right? And lastly, you have positive 2, and you have minus 3. So you end up with, oh, sorry, and you have another 2 here, right? So you have 4, right? 4 minus 3 give you what? 1. So the problem with the parametric equation, maybe you have different parametric equations and you have the same surface, right? So it depends. The original one is the Cartesian one, right? So this is the original one for the plane, right? So the plane has a unique equation in the rectangular coordinates, right? But it has multiple representative for the parametric ones, right? This is the main issue I have to tell you, right? Because some people think the equation is unique. Yes, it is unique when you go and stick to the original coordinates, right? But in the parametric equation, sorry, no, you may have multiple representative for the same one, right? Here, instead of calling the parameter s and t, he call it here u and v, right? Again, this is the first coordinate, which is x. The second one is u. The third one is z. So x, y, z. So this is a parametric equation, right? Okay. Originally, if you do this one and you divide it by 9, you divide it by 9, you divide it by 9, so you cancel out this one, right? And this one, you can write it out down as over 9 over 16, right? If you divide it, z squared over 9 over 10, it will be the 16, right? 16. The numerator of the numerator is the denominator, right? Okay. So why I'm writing this one and this one is equal to 1. This is exactly give you what? Ellipse, right? Okay. So if you are in 2 dimension, you think it is ellipse, right? But it is ellipsoid. Why it is ellipsoid? It means you have ellipse, and when you rotate it, right, it gives you a surface, right? This surface, we call it ellipsoid, right? It is ellipse. It is ellipse in 2 dimension. It is ellipsoid in the 3 dimension, right? Okay. And y is constant, right? Y is constant, is equal to v. Okay. So you have elliptical cylinder, right? Because y is constant. If you remember when we said z is equal to z, do you remember when we said this one? Here y is the same as y in this Cartesian or in this new representative, right? So you have a cylindrical elliptical cylinder parallel to the y-axis. Why parallel to y-axis? Because y is constant, right? So without changing the parametric into the original rectangular coordinate, you cannot fix what is this one represent what, right? So I make the conversion from the parametric into the rectangular coordinates to see what this parametric equation represent what. Catch it? So the 2 points from the parametric equation is not easy to know the shape, right? From the Cartesian, it is easy because you used to have the formula for different surfaces and different curves, right? In the two dimension, you have one parameter. In the 3 dimension, you have 2 parameters, right? Okay, this is the main issue. Catch it? This is exactly the ellipsoid cylinder. Look at this one. If you have this one, if I have one of these one, I have parabola, right? Okay? But why if we have 3 dimension, in the 3 dimension, I can represent R in terms of X and Y. Why I didn't add Z? Because Z is a function of X and Y, right? So I can write X, I, Y, J, Z, K in this case, right? So, and I know if I have a circle, I have one radius, right? If I have the cross section is ellipse, I have here A and B, right? We have 2 difference, right? So now I know how to represent this one in the Cartesian, and I know this one in the Cartesian represents something with the cross section as a closed curve, right? If you know this closed curve as a circle, you have the parametric relation here, right? If you have ellipse, it will be A here and B here, right? So now you can convert from the Cartesian into the new parametric ones, right? Okay. Now I will leave you this with this one, right? Do you think which coordinate you have to use here to change this one? We are in 3 dimension or 2 dimension? Good. So you have your cylindrical or spherical now? Yeah, because we don't have Z, right? We don't have, we have rho or radius and 2 angles, right? If you have radius and 2 angle, you have spherical, right? So just let me know what is this one. This is X or Y or Z. This is X or Y and Z, and change it and check this one. Why we are doing so? To prepare you for next week lecture, okay? This is the serval integral, right? So now you have the link, okay? Go for this link. This is why, you know, it takes time, but I open it for you already. Okay. I'm sorry. It's boring to have a link. Now you know the coordinate system, you know the parametric, you know the area element, the volume element. So please go for this link. Go through the surface integral yourself until we meet next week, and you have the solution here. All right. So go through, have an idea about it before we start to have it. Okay. Next week, inshallah, probably Monday, because we have the final exam.